All right, welcome to this explainer. Today we are absolutely completely demystifying the entire Arduino ecosystem. We're going to bridge that gap between the digital and physical worlds, taking what is basically just a bare piece of hardware and transforming it into a living, breathing project. Let's dive in. So, here's our roadmap for today. We'll meet the Arduino Uno, set up the software, learn the language, talk to the world, and then finish up with the classic blinking LED project. Section 1. Meet the Arduino Uno, the physical foundation. Okay, let's dive into this. What exactly is it? Well, Arduino is officially defined as an open-source electronics platform based on easy-to-use hardware and software. And honestly, easy is the operative word here. By stripping away all the massive, overwhelming complexities of traditional electrical engineering, Arduino acts as this brilliant abstraction layer. It lets you focus entirely on the interactive experience and the logic of your build, rather than getting bogged down in the raw physics of circuit design. Think of the 18-mega-3280p microcontroller as the brain of the whole operation. Branching out from it, you've got your digital and analog pins, which are essentially the nervous system sensing the world around it. The analog pins read varying real-world voltages, while the digital pins act as straight-up binary on-off switches. Rounding the whole thing out are the USB and power jacks. These are the lifeblood of the system, providing both the electrical power and the data pathway to actually get your code onto the board. Moving right along to Section 2, setting up the software, the digital environment. Now that we have our physical brain, we've got to set up the workspace. And it's a beautifully straightforward three-step process. You download the IDE for your operating system, install it, and configure it. Actually, quick pro tip straight from the source material here, make absolutely sure that Install USB driver box is checked during the installation. And always double check you've selected the right COM port in your tools menu. Otherwise, your computer won't even know the board is plugged in. Section 3, the language of Arduino. Basically how we instruct the brain. So every single Arduino sketch is built on this really stark architectural contrast. On one hand, you have void setup, which runs exactly once when you boot it up to initialize your pins and protocols. It's the prep phase. Then the microcontroller drops into void loop. This is your continuous action phase. It runs your main logic over and over and over again at lightning speed until you pull the plug. To actually fill out those sections, we're using a simplified C++-based toolkit. We store our data in variables, things like integers and booleans. We route the brain's decision-making through control structures like if-else statements. And crucially, we trigger the physical actions using core functions like digital write and delay. Section 4. Talking to the world. The senses. So the crucial point is that different hardware needs different ways to chat. Serial, or UART, is going to be your daily driver. It's absolutely perfect for printing text back to your serial monitors so you can debug your code. Then you have I2C, which is this brilliant protocol that uses just 2 wires to daisy-chain dozens of sensors together. And finally, for the really heavy lifting, like SD cards or Wi-Fi modules, SPI gives you that high-speed data transfer you need. And now, Section 5, the blinking LED project. This right here is the payoff, folks. Okay, picture this. We are now inside that continuous void loop we talked about earlier. We execute digital write, lead pin high. We're literally commanding the microcontroller to send 5 volts to that specific digital pin. At the exact same time, we're using serial.println LED is on to shoot a log back to our computer screen. And the result? Boom! It turns the LED on. I gotta say, there is something just incredibly rewarding about typing a line of text on your screen, hitting upload, and watching that digital logic instantly manifest as a real, physical light on your desk. It's like magic. Right after that, we write delay 1000. And this brilliantly illustrates how we control the flow of time. Get this. That 8-mega chip executes 16 million instructions every single second. By passing 1,000 to the delay function, we are essentially forcing this unbelievably fast brain to just twiddle its thumbs and completely halt its execution for 1,000 milliseconds. So it just sits there and waits for 1 solid second. Because, without that crucial pause, the microcontroller would toggle that LED so fast, it would literally just look like a dim, unbroken light to our human eyes. We wouldn't even see the blink. Now for the second half of our loop. We write digital write lead pin low. The voltage drops, the light goes out, and we immediately follow that up with another delay 1000, making the board wait in the dark for exactly 1 more second. And that completes the cycle. The LED turns off and waits. But remember the golden rule of void loop. Because all of this lives inside that function, the microcontroller hits the bottom and immediately jumps right back to the top. High, wait, low, wait. The result is this perfectly steady, rhythmic, endless blink. By bringing all of this together, the hardware, the software, the syntax, and the communication, you haven't just made a light blink. You've unlocked the foundational mechanics of physical computing. The blinking LED is really just your hello world. The tools are now in your hands, the physical world is waiting to be programmed, so what are you going to build next?